All right, so we're still sticking with the concepts involving circles, but today we're going to focus on how angles and arc measures are related other than the central angle, right? The central angle is equal to its intercepted arc. Right, and so just a couple quick pieces of terminology to define. And you're going to hear inscribed angle and intercepted arc today. And so an inscribed angle is an angle whose vertex is on the circle. And so here, angle B is an angle whose vertex right here is on this circle. So that's considered an inscribed angle. Right? Again, a central angle has a vertex at the center, an inscribed angle is on the circle itself. Right? Now, with regard to this same kind of diagram, when you look at that intercepted or that inscribed angle, there's a portion of the circle that falls in the interior of that angle. That's called the intercepted arc. Okay, so if we go down to the next slide, or the next box here for that term, okay, the intercepted arc is the portion of an arc that lies between, or lies in the interior of an angle. Okay, so we will refer to intercepted arcs for central angles as well. Okay, but the intercepted arc is the portion of a circle that falls in the interior of any angle. Okay, so here on this, if we look at these two, angle B or ABC is the intercepted or is the inscribed angle. And here on this second example here, arc AC is the intercepted arc. And again, it's assumed that you'll know what I'm referring to when I bring these up, including here in this next little box where we're going to talk about the measurement for this. So we've already talked about central angles are equal to those intercepted arcs. And for an inscribed angle is going to be 1/2 of the measure of its intercepted arc. And so if we call this arc measure right here M, and we call this angle, this inscribed angle A, you have two sort of perspectives to think of this. From the perspective of the angle, an inscribed angle is equal to 1/2 the measure of the intercepted arc. So if we're thinking in terms of the angle itself, A is equal to 1/2 of M. So there's your mathematical relationship. And there's a second way to, again, a second perspective for this that is the same relationships, but here if you're taking your intercepted arc, the intercepted arc is going to be double the measure of its inscribed angle. Bless you. So the mathematical relationship here would be M is equal to 2 times A. Now these are equivalent equations, right? One's just solving for A, one's solving for M. All right, so see if you can apply that relationship here to both parts of this question on this slide here. All right, so we have two, again, both perspectives are handled in this question. First we have this angle T. So if we have the perspective of the angle, an inscribed angle is 1/2 the measure of its intercepted arc. So if we take the intercepted arc of 104 and cut that in half, that gives us our measure for T, which is 52 degrees. Okay, inscribed angle is equal to 1/2 the measure of its intercepted arc. And now shifting gears to the arc measure, QT. If we're looking to find this arc measure, the arc measure is double the measure of the inscribed angle. So here we would take that inscribed angle of 66, multiply by 2, and that's going to give us the measure of this arc, which would be 132. All right, so those are sort of the main relationships that we're going to be looking at here today, is that inscribed angle is 1/2 the measure of its intercepted arc. All right, so the remaining slides kind of highlight some properties associated with this. Okay, the first is, what would this mean then if two inscribed angles intercept the same arc? So if this arc right here is m, then that means that angle C is going to be what fraction of m? Inscribed angle is half the intercepted arc. So C would be 1/2 of m, and what would angle D be in terms of m? Same thing, right? It's also 1/2 of m. So what you see right here is that if you have multiple inscribed angles that intercept the same arc, those are going to be congruent to each other. So here, angle C and angle D would be congruent because they inscribe the same arc. And that should be a relatively intuitive relationship. See if you can answer this question based on that. So there may be questions where you're just being asked to find one of these and not both. If that's the case, if you need to know what angle S is, angle S inscribes or intercepts the same arc as the inscribed angle R, so that means they're going to be the same. So you can identify that. If you need to find the arc measure, like we are asked in this one as well, then the arc measure is equal to twice the measure of its inscribed angle. So 23 times 2 is going to be the measure of this, or 46 degrees. Okay, so again, that's building off of that same exact relationship that the inscribed angle is half the intercepted arc. Right, so before I move to the next slide, I do want to just kind of talk about something really quickly, and that is what happens if you take a right angle and you inscribe a right angle in a circle? And what is that going to form? What arc measure is going to be cut off here? The intercepted arc is double the inscribed angle, so double 90 gives you 180 degrees. And so what is 180 degrees classified as arc? Semicircle. So what that means is that if you have a right angle that's inscribed in a circle, it's going to cut off a semicircle. And so that's going to allow you to see that this forms a right triangle with the diameter as its hypotenuse. And this is an example of an inscribed figure. An inscribed figure means that all of the vertices lie on the circle, which then means that every vertex is an inscribed angle. So there's an inscribed angle. We have this other acute angle of the right triangle is inscribed. The right angle itself is inscribed. Okay, so an inscribed, this is a triangle inscribed in a circle, just means that all of the angles of that figure are inscribed angles. All right, so any properties of right triangles will work for this type of a problem. Okay? Which takes us to this next relationship that says, if you have a right triangle inscribed in a circle, and then it's what we just saw. Then the hypotenuse is the diameter. And that's based on the inscribed angles that we just talked about. So here, if we have a triangle, an inscribed triangle that is inscribed in this semicircle, then we know that this has to be a right triangle as well. So this also tells us If that or if an angle is inscribed in a semicircle. Oops. Okay. So if an angle is inscribed in a semicircle, then it is a right angle. Okay. Or if a triangle is inscribed in a semicircle, it's a right triangle. Okay. So see if you can answer these two questions using the concept of a triangle inscribed in a semicircle is going to be a right triangle. So working through the properties of triangles, which we discussed in some earlier chapters. Once again, you know that you have this inscribed triangle. D is the center of the circle, so you see that it is inscribed in a semicircle, which means this is going to be a 90-degree angle. And if that's 90, then the other two angles, the acute angles of that right triangle, have to be complementary or add up to 90 as well. And so angle C is just going to either be thought of as 90 minus the other acute angle 32. So that's going to give you a measure of 58. Or you can think of it, if you want, as the whole triangle sum, which would be the calculation 180 minus 90 minus 32. Those are the two angles that are provided in that right triangle. And so that would also leave 58 degrees as your answer. And so you could use any of those answers or calculations. For the next problem, again, what you're seeing is if you have a triangle inscribed in a semicircle, because D is the center, we see that that is the case here, that this is going to be a right angle. And so you should simply take the expression 30x, set it equal to the degrees of a right angle, which is 90, and then solve. And when you do that, the powers or factors of 10 cancel, 3 goes into 9 3 times. You're being asked to solve for x in that case, and so that would be your answer. Right. The final relationship that we're going to look at here continues to be built on these inscribed angles, and that is we just looked at if you have a triangle inscribed in a semicircle. What happens, though, if you have a quadrilateral inscribed in a circle? Okay, so if you have a circle where you have four inscribed angles, right? So this is a quadrilateral inscribed in a circle. If we look at, let's say, this measure and this measure. If we're trying to compare here these two opposite angles, well, if angle A intercepts this arc right here, in terms of A, what does that make this arc equivalent to? An intercepted arc is what compared to its inscribed angle? It's double that, right? So this whole intercepted arc is going to be 2A. And if we look at the same thing for angle B is an inscribed angle, so it intercepts this portion of the circle. And that means that that whole arc measure would be twice B. Okay, so in order for us to find what's the relationship between A and B, these opposite angles here, what we can do is we know now that 2A plus 2B equals a full rotation around the circle, which is how many degrees? 360. And so if we divide everything by 2, we get A plus B is equal to half of 360. And so we see the relationship that we need to for this inscribed quadrilateral. Okay, if you have a quadrilateral inscribed in a triangle, so a quadrilateral inscribed in that circle is going to have opposite angles that are supplements of each other. And remember, the supplementary means that they add up to 180 degrees. Okay, so in this particular case, the measure of angle D plus the measure of angle F, these opposite angles, are equal to 180. We also know that the measure of angle E and the measure of angle G would equal 180 degrees as well. Okay, and so that would be your relationship there, again based on just inscribed angles. So try these last two questions here. See if you can work through and find what the unknown measurements are based on that property, that if a quadrilateral is inscribed in a circle, and then opposite angles add up to 180 degrees. All right, so the first one is a little more straightforward, right? You're just looking at opposite angles. So if I want to find angle A, I look opposite it of 29 degrees. We know that those are supplementary, so 180 minus 29 is going to be your answer for that. If you actually calculate it, you get 151 for the angle measure. And finally, or the second one, here, angle B and D, you look opposite one another. And so once again, they're supplementary. So 180 minus that 39 is going to give you your angle measure. And so if I just change that 29 to 39, I see that it's 141 for my second angle, or the second missing angle B. For the problem below, you're solving the same idea here, but now it's going to have expressions in them. So if we look at these opposite angles, B and D, we know that their expressions, x and 11x minus 192, has to add up to 180 degrees. And so if we combine what we have, 12x, add 192 to both sides. And you can either leave it as a full calculation if you want, or you can do the calculated value. So here, 372, and then divide by 12. And that's going to give you your answer of 31. Bless you. Okay, so x is 31 in that particular case. And to find our y values, we look at these opposite angles A and C. We know that 8y and 12y add up to equal 180 degrees. And so 20y equals 180, divide by 20. The factors of 10 cancel, 2 goes into 18 9 times. And so here it's a little bit simpler mental calculation, and you would get your value for y to be 9.